Do you know what PPV is? If not, this video was created for you. The pair packet value concept, or simply PPV, provides a core stateless way to control resource sharing among traffic aggregates. A traffic aggregate could be a simple TCP or UDP flow, the total traffic of a subscriber, or the packets generated by an application or an application group. With the advent of technologies like 5G or fiber to the home, high-speed internet access became possible for millions of end users. This results in much higher load on the access aggregation network than before and moving bottlenecks to routers in the core network from the edge. Scalable resource sharing solutions that are simple, flow whenever, and enable rich set of policies are required to support quality of service in congestion situations in future access networks. In the pair packet value concept, the resource sharing policies are implemented by a packet marking mechanism that assigns a packet value, actually a simple number, to each packet. The packet value expresses the importance of the given packet in the traffic mix. Packet marking can be done for the different traffic aggregates independently and thus can be implemented in a distributed way. The routers in the network then aim at maximizing the total value delivered without having any additional information on the traffic aggregates and the policies to be applied. They use a single packet buffer. For example, when a packet arrives at a full buffer, packets with the smallest packet values are dropped to make room for a more valuable packet. Either the incoming packet or packets from the middle of the queue can be dropped in this case. Let's see an example. In an access aggregation network, resource sharing is generally applied on the downstream traffic. Its goal is to provide fair or weighted fair resource sharing among the subscribers. In PPV, for each subscriber, packet marking is done independently at the border of the access network. A packet marker instance assigns comparable packet values to each packet of the traffic aggregate it is responsible for. In this example, the different values are illustrated by different colors. Then routers inside the network solely use the carried values to decide if a packet is dropped or forwarded in congestion situations. No per flow or per subscriber states are required to store in the routers. This trivial mechanism is called as the drop minimum packet value first. Okay, let's see how this strategy can be used with appropriate packet marking to ensure resource sharing in congestion situations. We have learned that the PPV mechanism is based on the packet marking. For each traffic aggregate, we have a dedicated packet marker instance that computes and assigns the packet values. In the following example, we assume a single constant bitrate flow called flow number 1 as a traffic aggregate. The marking is based on a function that we call throughput value function, or shortly TVF. Every traffic aggregate has its own TVF to be applied for marking. As we will show later in this video, different resource sharing policies can be expressed by applying different TVFs for the different traffic aggregates. In this example, we only distinguish 10 different packet value levels from 1 to 10. Axis X represents the throughput at the packet marker. In our case, this is the sending rate. For each throughput value, the associated packet value can be seen on axis epsilon. The throughput value function defines the expected contribution of packets with given packet values in the total traffic of the flow. In our example, the sending rate of our single flow called flow number 1 is 80 megabit per sec. Packet value is 10 between throughput 0 and 10 megabit per sec, which means that if we filter out packets with packet value 10, the throughput share in the total traffic of flow number 1 should exactly be 10 megabit per sec. Of course, in practice, different packet sizes may cause some deviances from this exact value. Similarly, the contribution of packets with value at least 9 is 20 megabit per sec. With at least 8 is 30 megabit per sec, with at least 7 is 40 megabit per sec, and so on. This animation shows how the throughput of a traffic aggregate can be controlled by dropping packets below a specific packet value threshold. The different colors represent different packet values. Dark blue denotes the largest packet value, which is 10, and dark red is the packet value 1, which is the smallest. The sending rate of the source is 8 packets per second, and there is no bottleneck in the system. To demonstrate the role of packet values, We first filter out packets below value 7, representing light green color. As a result, all the packets with colors representing smaller values are dropped. At the receiver side, we can see 4 packets per second throughput. Then we increase the threshold to 8, dropping more packets and resulting in 30 packets per second forwarding rate. As the threshold is increased, more and more packets are filtered out. Remember that, in case of congestion, routers always drop packets with the smallest packet value. This mechanism automatically leads to an observable threshold value below which all the packets are dropped, while above that all the packets are forwarded. If the congestion level is increasing, the imaginary threshold value is also increasing, while in case of decrease in the congestion level, the threshold value is also decreasing. This is the expected behavior a packet marker must satisfy. Let's go back to our original example. The bottleneck capacity is 100 megabit per sec, so there is no bottleneck in this setup, and thus 80 megabit per sec throughput is assigned to flow number 1. Let's see what happens if we change the bottleneck capacity to 60 megabit per second, which is less than the sending rate of flow number 1. Obviously, the throughput of flow number 1 should be the bottleneck capacity, that's 60 megabit per sec. To reach this, the bottleneck router needs to drop some packets. But which packets? Since we have a single flow and we know how packets are marked with a throughput value function, dropping the packets with minimum packet values leads to an observable packet value threshold below which all the packets are dropped. In this case, the threshold value is 5 and the resulted allowed throughput of the flow is 60 megabit per sec. This threshold value is called congestion threshold value, or shortly CTV. For any congestion situation, the applied drop minimum packet value first strategy automatically leads to a CTV that can be observed in the system. Important to know that CTV is not a parameter of the system. We don't have to set it manually, but it is a natural result of the drop policy routers apply. In this animation, we demonstrate how this dropping threshold called CTV can automatically set by the dropping mechanism of PPV. The sending rate of the single source is 8 packets per second, while the bottleneck capacity is 6 packets per second. After the buffer is filled, the CTV converges to packet value 5 rapidly. The observed congestion threshold value is also shown as a black bold vertical line in the packet value palette. The packets are only dropped with colors on the right side of the threshold. Now we know how the throughput of a single flow can be controlled. Let's consider a second unresponsive constant bitrate flow in the system. The bottleneck remains 60 megabit per sec. The sending rate of the first flow is 80 megabit per sec, while the second is 50. Both use the same throughput value function to mark the packets. How the bottleneck can be shown among them? Since the same TVF is used and the sending rates are high, we expect fair share of the bottleneck capacity. In this case, dropping packets with minimum packet value leads to a congestion threshold value of 8, resulting in 30 megabit per sec allowed throughput for both flows. This animation shows a similar situation where the sending rates are 8 and 6 packets per second, while the bottleneck capacity is 6 packets per second. The bottleneck router can buffer 10 packets. After some unstable initial phase needed for filling the buffer, the resource share among the two flows stabilizes around a fair resource allocation. In addition to fair sharing, different policies can also be expressed in the PPV method. Let's consider that we use a difference throughput value function to mark the packets of flow number 2. For this second flow, the packet values drop 2 times faster with the throughput than in the original TVF. The two TVS enable us to differentiate between users, subscribers or flows, creating gold and silver groups, for example. Our expectation is that in congestion situation, the gold flow should get better access to the shared resource than the silver ones. In this example, the gold flow uses the original TVF, while the silver, less important flow uses the second one. The aim of this TVF design could be to provide 2-to-1 resource share between individual gold and silver flows. With other terms, a gold flow may have twice the throughput of a silver one in case of congestion. The bottleneck capacity is 90 megabit per sec in our case, while the sending rates are 80 megabit per sec. The drop policy of PPV leads to a CTV of 5 in this case, allowing 60 megabit per sec for flow number 1 and 30 megabit per sec for flow number 2. A similar situation is demonstrated in this animation. The two flows send packets at rate 8 packets per second, while the bottleneck is set to 9 packets per second. They use two different TVFs. The source on the top is gold flow, while the bottom one is a silver one. After the unstable initial phase, the resource share converges to the expected 2-to-1 ratio. The silver flow gets 3 packets per second throughput, while the gold gets 6 packets per second. Thank you for watching this video. More details on PPV are available at our website ppv.iate.hu.